Howdy there, once again YouTube. This is part 1 of Amateur Seismology Basics, Misconceptions, and Tools. I'm Ben Ferraiuolo, and I do apologize I have not done a video in a while. The reason for this is because I have been vigorously researching about seismology, and I've learned that some of what I have said in my previous videos is completely wrong, while other things I have stated were spot on. In part 1 and part 2 of this video, I will simply show you how to read a seismograph, learning network and station codes in order to access seismic data, the IRIS time series database archive, which archives most seismic data, and the 3 new seismic analytic tools I have discovered that have helped me learn a lot in the past few months. Some information will not make it into this video because there's a lot, so I suggest you do what I did if you are interested and do a lot of personal research on your free time. You can also email me at the email address in the description box below if you ever need help. If you really are interested in monitoring Yellowstone and other areas for signs of unrest, the best way to do that is become a sort of amateur seismologist and learn the basics of waveform characteristics. Keep in mind, the goal of this video is to hopefully give you some of the tools and some of the information required to fully understand how certain seismic events are caused and how to watch out for them. Trust me, you will not get the hang of it right away, and you will always be learning. I still have a crazy amount to learn about seismology, to be honest, some of which makes my head spin. Seismic signals and ground deformation will be our main sign of whatever may be approaching in the future, not just at Yellowstone, but at other volcanoes as well. Now don't get me wrong, it can be extremely frustrating at times, but patience and passion will help you through it. I still have an insane amount of information to learn regarding seismic waveforms themselves. To start off, a waveform is simply the line that makes up a seismic trace. And in other words, a seismic trace is a seismogram. Another thing to add is the confusion people have when comparing seismographs. Now, if you see something appear on a seismograph, you cannot immediately say that it is an actual underground event, like an earthquake or harmonic tremor or whatever. For the record, the word harmonic tremor is used way too often nowadays. It is losing its meaning because of people who cry wolf. I mean, not necessarily on purpose. Someone could have actually thought it was harmonic tremor. But I'm just saying, it's being used way too much nowadays. I have to say, when I first started out, I thought everything was harmonic tremor. I really did. But you remember, didn't the wolf come at the end of the story for real and then eat the boy because nobody would listen? So remember, seismometers simply record all vibrations that reach the instrument. The stronger the vibration, the farther it will travel. Some vibrations can travel hundreds of feet, even farther if it's stronger. And yes, even strong winds can appear on seismographs, depending on 3 things: distance, intensity, and the depth of the instrument. You must compare the timings of the start and the timings of the end of the event in question on at least one, and I say very least, one other neighboring seismograph. It also helps to be able to zoom in on a seismic trace to see the waveforms that online seismographs lack. Now, wait a second. Some people are thinking, wait, how do you zoom in on one of these seismographs? I didn't know you could do that. Well, the 3 seismic tools I will talk about in part 2 allow you to spread out the waveforms, elongate the amplitudes, filter the waveforms to show specific frequency ranges, and much more. The more neighboring seismograph stations you use, the easier it is to tell if it was surface noise. Anthropogenic simply means that it was caused by humans, or an actual seismic event. Another misconception is that magma intrusion has been happening almost daily or weekly lately at Yellowstone. Well, when magma intrudes, even when it has a free pathway that is not blocked, earthquakes will occur. I mean, also in rapid succession, not just an earthquake here and there. But if magma intrusion happens, it will break away the rock around it. It's how magma works. I mean, because magma is hot and viscous, which means thick, compared to water, and will almost certainly always break away rock during its ascent, causing volcanic earthquakes, or low-frequency earthquakes, or hybrid earthquakes, or even, right before an eruption, volcanic tremor. I have never heard of magma intrusion occurring without breaking away the rock that surrounds it, creating multiple earthquakes in a short period of time, also called a swarm. In a few minutes, I will show an example of different types of waveforms caused by different types of earthquakes. Now, don't get me wrong, magma intrusion has occurred at Yellowstone, at the very least just twice this year. Although the most recent case on July 5th was very short-lived and not sustained, so there is of course no threat of any imminent volcanic eruptions at Yellowstone. However, you never know. That could always change in the blink of an eye. That's why I study this place so intensely. I studied the July 5th event almost 6 times already, and am still fascinated by it. So you know how some people don't like or do not understand microvolts? Well, if you analyze the seismic data, like how I'm going to show you soon, microvolts do not matter at all. Also, please research about P and S wave arrivals in regards to earthquakes. I am still learning about those too. So what we are going to do now is pick 2 stations and lay them out in Jamaseus. One station prone to surface interference, and one that is not as susceptible, right next to each other. Borehole 944 in Grant Village is, surprisingly, prone to a lot of surface activity, and YLT, see right here, here's B944. And so we'll use this, and we'll use YLT, a station which resides just a few miles north, is not prone to much surface interference. I mean, once in a great while it will show something, but usually it's a very good seismograph. It's one of the more dependable ones out of all of these. Now here we have borehole 944 in Grant, and YLT, which is just about 5-10 miles or so, not that far from borehole 944, which means if something is seismic, these two will pick up the same thing, almost always. Now in part 2 of this video, I will show you guys how to use Jamaseus. If you would like to see that now, please find the video with the same name on my YouTube channel, except it starts with P2 instead of P1. Now, I want to show you this for example. You see this right here? Okay, so this is the same time frames. In Jamaseus, it always keeps the same time frames for whatever source you have. Magnification 60, magnification is 60. So it's all set to the same exact thing. Now this is why you don't have to worry about microvolts, because you can set the magnification yourself. Microvolts do not matter anymore, unless you're obviously looking at the online seismographs. But look, this is borehole 944. Here is some surface noise right here. If this was a seismic event, it would show right here, but instead we see nothing. This, that is surface noise. It showed on a borehole. Now, for example, this right here and this right here showed on both the seismographs. So it looks like this right here and this right here is an actual seismic event. These probably are a little too small maybe, but this down here doesn't show. So it is possible to have surface noise on boreholes. It is possible. I never thought it was, but it is. And surface vibrations can travel a lot farther than I was originally led to believe. Let's keep going. Here's something that's a little bit larger. See right here? This is a good larger amplitude surface noise because it doesn't show right here. See? These 2 stations are not that far apart, yet some larger amplitude activity appeared on borehole 944, but did not appear at all on YLT, even though YLT should be close enough to feel this activity, if indeed this activity were coming from underground. Surface noise is possible, guys, even on boreholes. Research how far seismic noise from the surface can penetrate the ground. The online Wiley library is also a great source I use for access to many intelligent articles. Now here's an example of common activity usually seen every other day or so near Mount Rainier. Each type of ground shaking event usually generates a unique seismic signature that can be recognized and identified as having been written by a specific event. Match activity with the signature. This is a debris flow, maybe like an avalanche or something. This is a teleseism, a distant earthquake. This is a tectonic earthquake near Mount Rainier, and a tectonic earthquake beneath Mount Rainier. I'm guessing that's probably a volcanic tectonic earthquake. These are rock falls, so some landslides, and glacier sliding noise. Yes, glaciers on top of volcanoes can cause tremor. Isn't that surprising? So the waveforms do not look too detailed, so I'm thinking the time period from about here to here, and from here to here, from end to end, is about 2 minutes or so. Remember, the time scale usually shown at the bottom of waveform examples, and even seismographs themselves, is very, very important. Let's take a simple 2.5 earthquake for example. Now, you will see a lot more detail if the time period is 1 minute than if it were 5 minutes. Get what I'm trying to say? Now here's actually a great novice video created by IRIS about common seismic events. IRIS is the Incorporated Research Institutions for Seismology. The location is Mount St. Helens from the Seismograph. Remember, there is one thing to always keep in mind. Surface events and underground seismic events have one thing in common. Waveform characteristics can vary from location to location based on a multitude of factors such as bedrock, the strength, multitude of factors. For the sake of time, I will not play this video, but I highly suggest that you watch it. It's very quick, and you can just download all, and it has a few files in there of the seismograph itself, I believe. It's pretty cool. It helps you to understand some of the surface noise that can occur, such as a helicopter landing, which looks very familiar to me and makes me think that helicopters have been landing in Yellowstone a lot lately. And a link to this will be posted below. It's quick and it's very easy to understand. Now we are going to look at a few different types of waveforms you will encounter when monitoring potential volcanic or tectonic hazard areas. Remember something when comparing waveforms. Get as much information as possible, such as magnification, the highest amplitude count. Amplitude is the height of any given seismic trace, and time period. The time period when given will be at the bottom of any seismograph or any seismic trace, such as right down here. The time period for this one example, from end to end, seems to be about 45 to 50 seconds. In retrospect, the University of Utah seismographs they post online are very small. They're constrained by pixels and run 30 minutes per line. And this is seconds, guys. No wonder we can't see any detail on the online seismographs. Well, now we can by using the 3 seismic analysis tools I will talk about mainly in part 2. First, we see a volcano tectonic earthquake. This can be caused by normal tectonic stress above or alongside any volcano. However, VT earthquakes can be caused by the upwelling of the ground caused by magma. Do you notice the sharp arrivals throughout the waveforms? I mean, compared to this and this? This is basically what a normal tectonic-induced high-frequency earthquake looks like. Now I'm going to read this article real quick by USGS about the rest of the waveforms. Many processes in and around volcanoes can generate earthquakes. Most of the time, these processes are faulting and fracturing that does not lead to an eruption. However, volcanic earthquakes do occur as magma and volcanic gases rise to the surface from depth, which involves significant stress changes in the crust as the material migrates upward. See, that's what I said, but they said it better. Volcanic seismologists study several types of seismic events to better understand how magma and gases move towards the surface. The VT earthquakes represent brittle failure of rock, the same process that occurs along purely tectonic faults, such as the San Andreas Fault. At volcanoes, VT events can occur due to normal tectonic forces, changing stresses caused by moving magma, and the movement of fluids through pre-existing cracks. Distinguishing between these various processes can be very tricky, and often requires data from other disciplines, geodesy, hydrology, gas geochemistry, and geology to work out what's going on. Number 2, long period or low frequency earthquakes. These earthquakes, which I have to say have been seen every now and then at Yellowstone, and hybrid events. This is what I've been seeing recently. These 3, VT, low frequency, and hybrid events, have been occurring at Yellowstone the past few years. They are earthquakes that are caused by cracks resonating as magma and gases move towards the surface. They are often seen prior to volcanic eruptions, but their occurrence is also part of the normal background seismicity at some volcanoes, and their occurrence does not necessarily indicate that an eruption is imminent. I have to go along with them on that one. That's very true. But trust me, it can lead to an eruption at times. LF events also can be produced by non-magmatic processes, most notably glacier movement. As stated, low-frequency earthquakes at volcanoes are also caused by the injection or withdrawal of magma resonating through above cracks or fissures. If so, then people cannot deny magma intrusion has occurred at Yellowstone, since many low to mid-frequency earthquakes have been seen, most notably on July 5th, 2018. Next is a hybrid earthquake containing both high and low frequency arrivals. Notice how some parts of this earthquake appear both tectonic and volcanic in nature? These have also been witnessed recently at Yellowstone. They appear to be more common at Yelly than low frequency events. Now this here is a VLF earthquake, or very low frequency earthquake, and it is a slow one that can be considered a subcategory of low-frequency earthquakes. They can be seen during slow-slip tectonic events. And then the last one is tremor, a continuous high-amplitude seismic signal that can be caused by multiple processes, including long-lived resonance due to extended flow of magma movement through cracks, continuous occurrence of VT or LPLF events that are so closely spaced in time that they cannot be visually separated, and explosions. So this is what to watch out for hours, guys. I mean, this could go on for hours or days or weeks, and most notably sometimes leads to an eruption. Now, sometimes it doesn't, but why does this sometimes lead to an eruption? Well, long-lived resonance due to the extended flow of magma. Sometimes when magma intrusion occurs, it won't lead to anywhere. It'll just, create a weak point so that eventually down the road an eruption will happen. But if it's, let's say we see a long-lived resonance of extended magma flow at Yellowstone, and it's still going, it ain't stopping for days and days and days and days, that's when you get really worried. But then again, I have to say that might not happen at Yellowstone either. We have no idea what's going to happen at Yellowstone. Nobody does. Most volcano-related earthquakes are too small to feel, generally quite shallow, usually within 10 kilometers, 7 miles of the surface, and can occur in swarms consisting of dozens to hundreds of events. Most swarms usually don't lead to eruptions, but most eruptions are preceded by swarms. Therefore, during any heightened period of seismic activity at a volcano, seismologists work round the clock to detect subtle variations in the type, location, and intensity of seismic activity to determine whether or not an eruption may occur. I hope to be one of those seismologists someday. I would love to be a volcanic seismologist and work at either Yellowstone or Mount Rainier. I would love that. So here we have some more waveform examples. On the left, we have seismograms, also known as seismic traces. Remember, waveforms are what make up a seismic trace. And on the right, we have the spectra analysis of each event. Also, each event is labeled. Now, with spectra, this is not like a spectrograph that you are used to, such as the common spectrographs, which with frequency range labeled on the left and the time period at the bottom. This is a spectra analysis of each event. The bottom line from here to here, see this, is the frequency range instead of the time period. This shows us what the majority of the frequencies were for each event from arrow to arrow. That is why they have these arrows here. First, we have an earthquake induced by glacial stresses. Next, we have an even larger ice quake. Next, we have a distant small earthquake and a VT earthquake. Now, here is a deep long period event. Notice with the deep long period earthquake from this arrow to this arrow, no frequencies surpassed 5 Hz. You see that? Remember, harmonic tremor occurs between about 0.7 Hz and 5 Hz. It all depends on location. The last two events here are surface events, avalanche and rockfall, and rarely have to be worried about if monitoring Yellowstone. Now, stratovolcanoes, on the other hand, such as Mount Rainier or Mount St. Helens, can show these types of seismograms every once in a while. Now, here is one of the more popular seismograms example. Keep in mind, from here to here, they say is 10 seconds. So, from here to here, I'm going to say maybe about 15-20 seconds. So from about here to here would be about a minute. So this is probably about the same length you would see on Jamaseus if you do it 1 minute per line, which I'll show you how to do in part 2. Remember, time periods really do matter. Again, number 1, we see a simple tectonic earthquake caused by local faults. Notice again the sharp arrivals that every now and then are missing from the more volcanic-induced events. Here is a recent example of a very shallow, pure, non-volcanic induced earthquake from July 10th, 2018 near Brewster in Washington State. Again, please notice the sharp arrivals even amongst most of the coda. A coda is simply the diminishing end tail of an earthquake signature. Here is another recent example from July 13th, 2018 of a magnitude 1.4 earthquake that struck about 15 kilometers deep between Selah and Yakima, Washington. Once again, sharp arrivals indicating most likely no volcanic processes had to do with this earthquake. Notice something. See here how it says the magnification is set to 33 right here? Well, the magnification here is set to 15. So the picture I just showed of the waveforms from the 1.4 earthquake at Yakima was enhanced to twice the size of the earthquake pictured here. Remember, always pay attention to time periods and magnifications if they are stated. Next on the list is a shallow volcanic earthquake. Shallow earthquakes located under the dome at depths of less than 3 kilometers which produce medium to low frequency seismic arrivals. I would not be surprised if some of these have occurred at Yellowstone recently. Oh, wait a second. Well, this looks a little familiar. The bottom here is the same time period, but from YML, Mary Lake, which is about 12 miles northwest of YLT, this station that recorded this right here. Now, on the example, it said the shallow event was about 10 to 15 seconds long. Well, that can be from about, here to here. Remember, the strength of an event will affect the length and the height of the waveforms. This was taken from the 40-minute case of likely magma intrusion that occurred at Yellowstone, July 5th, 2018. Now, I'm not saying this is the exact same shallow event that I just showed in the Seismograms example, but it's definitely looking similar. This was definitely not tectonic, guys. I highly doubt that, especially with some of the other seismic signatures that showed up in this 40-minute long swarm. I still conduct analysis on this event to this day. It fascinates me. The next event given is this example of a type of surface event, such as gas and tephra events, rockfalls associated with dome growth, and snow and rock avalanches from the crater walls, which produce complicated signatures with no clear beginning or end. Imagine a fixed position, such as a seismometer, recording vibrations. Now imagine a car approaching and receding away from the fixed location. Not all surface noise looks like this, but this is kind of a good example. Last, but certainly not least, is harmonic tremor, which is a long-lasting, very rhythmic seismic signal whose origin is not well understood, but which is often associated with active volcanoes, and usually is seen just prior to an eruption. Now, harmonic tremor is the go-to phrase for people who don't know much about seismology. Many people have done it, including me. I'm not out of that category, guys. Trust me, I've done that so many times. But remember the boy who cried wolf. Always be on the lookout for harmonic tremor, even in places unexpected. But remember, some types of surface interference can look similar to, in regards to waveform characteristics, harmonic tremor. As stated, its origin is not well known, and seismologists, surprisingly, still argue to this day about what specifically causes its signal. However, if you see it appear, especially on multiple neighboring seismographs, and it is sustained for quite some time, such as maybe 4 hours or more, and accompanied with many earthquakes and deformation, it is a sure sign an eruption may be imminent. To me, imminent eruption means within a few days. Impending may be a little more flexible, as in a month or so. Personally, I am monitoring Yellowstone for signs that precede large volcanic eruptions by years. Sometimes, at some volcanoes, quick, non-sustained magma intrusion can occur, without leading to an immediate eruption years before activity reaches an actual eruption. Here is one last example of some waveform characteristics. So, what do you think the problem is with this example? It is way too simple. The goal of this example, I believe, is to give a simple example of waveform distribution. The first is a tectonic earthquake with, once again, sharp arrivals in quick succession. You see that? Very close to each other. The second is a low frequency, sometimes known as long period earthquake, with wider oscillations. The third is harmonic tremor. However, I have no idea which type of harmonic tremor they are expounding on. I've never really seen an example like this on an actual seismograph before, so I don't know. Real quick, here is a video that I found kind of helpful. It's a very simple, very novice video for beginners. This illustrates what happens at a volcano before it erupts, most notably a stratovolcano. Sadly, the time frame and the scale is not to be fully relied upon. This is to simply show the basics of what happens and what appears on a seismograph at a typical volcano months or days before a notable eruption. Please subscribe to Iris Earthquake Science channel on YouTube. They really do have some awesome info that even beginners can understand. The link to their channel is below in the description box as well, under links. And don't forget, guys, if this video is too long, you can always go down in the parts in the video to kind of maneuver through the video to see the info that you actually want.
Most earthquakes associated with young volcanoes are related to the movement of magma deep beneath the volcano and may indicate that a quiet volcano is becoming active. Although large eruptions are often preceded by several significant earthquakes and many small rock-breaking quakes, there's also a continuous release of seismic energy associated with the underground movement of magma. Volcanic tremor is a seismic vibration caused by the pulsing of pressurized magma and gas and can last for minutes or days. The seismogram is of longer duration and more continuous than rock-breaking earthquakes of the same amplitude. Earthquake swarms recorded by seismometers and the ground deformation monitored by tilt meters help scientists determine the location and depth of moving magma beneath the volcano, which in turn gives scientists information to issue hazard warnings.
So that was pretty interesting. Notice the earthquakes. It seems tectonic earthquakes occurred first due to the upwelling of the ground from the magma trying to escape. Now, just real quick, guys, this was just an example. Things at volcanoes can happen totally different, because each volcano is kind of like a fingerprint. Every single one's totally different, and the warning signs associated to each volcano when it erupts is totally different. As we follow the magma's ascent to the surface, it creates vibrations through cracks or fissures, created either by past events or current ones. Once it reaches quote-unquote full capacity, it starts to break away the rock at a fast pace just prior to an eruption, causing almost continuous earthquakes. This continuous rhythm of earthquakes, regardless of size, is called volcanic tremor. Now, harmonic tremor, though its actual source remains a mystery, could be the cause of fast-flowing magma through lava tubes present from previous eruptions. Just a theory of mine. Harmonic and volcanic tremor has most likely, again I say most likely, it could have, but most likely never been witnessed at Yellowstone since no volcanic eruptions have occurred. But don't get me wrong, volcanic seismic events have happened at Yellowstone multiple times in the past few years, guys. So you're not off the hook yet. Remember, Yellowstone is extremely larger than any volcanoes people are used to. Therefore, it is safe to assume it will take years and years to recharge instead of months and months, like stratovolcanoes. However, this place is very dynamic, so please keep your eyes out for concerning activity. No one has ever witnessed, especially with seismic instruments, a supervolcano caldera charge before. The collective warning signs could be drastically different than what anyone has seen before. I will leave a link in the description box below about a study put out by Arizona State University saying how they possibly discovered Yellowstone could charge within a few decades rather than centuries or thousands of years like previously thought when the warning signs appear. Interpreting waveforms. Again, I will leave this link in the description box below. Web Recorder images digitally simulate seismograms recorded at the Earthquake Studies Office. Seismograms are records of ground motion at seismograph stations in the Montana Seismograph network, made each 24-hour period. Seismograms are read like a book, from left to right, then from top to bottom, just like a book, guys. These are the directions on the images that time increases. As with a book, the right end of any horizontal line connects with the left end of the line below it. The color of each horizontal line has no significance, but makes the web recorder, the image, the seismogram, easier to read. The vertical lines are spaced at 1-minute intervals. The time of day, hours, minutes, is indicated in the left margin in Mountain Daylight Time on the hours, and at the right margin in Universal Coordinated Time, Greenwich Mean Time, on the quarter hours. When a seismic event occurs, seismograms show ground motion at the location of the recording instrument that typically lasts from several tens of seconds to many minutes, depending on the size of the event and its distance from the recorder. The height of the waves on the seismogram, wave amplitude, is a greatly magnified representation of the actual ground motion. The magnification, remember how in John Macias you could change the magnification? The magnification of some stations may be greater than 100,000 times. An earthquake recorded on a seismogram has recognizable characteristics. Typically, you can see the arrival, the compressional wave, P, travels fastest through the earth, and S, and the shear wave, somewhat slower. On our seismograms, you may see local earthquakes in western Montana, regional earthquakes from surrounding states, Pacific Northwest, and earthquakes elsewhere in the world having a magnitude greater than 5.5 on the Richter scale. For distant earthquakes, be sure to look at the broadband seismogram. Blah, 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 blah. Let's go down here real quick. Remember, you guys can read this too if you want. Not all the waves on seismograms are caused by earthquakes. Anything that produces ground vibrations is recorded. For example, vehicles on nearby roads, which is why they try to locate their seismometers well away from roads, wind noise and thunder, or animals passing nearby, a herd of elk, for example. Man-made mine blasts are also recorded, such as the ones from Montana tunnels, Golden Sunlight, the Continental Pit, and Yellowstone Talc. The uniform amplitude ground vibration at certain stations, BZMT, STMT, is caused by nearby equipment. Some other non-ground motion signals are common. Pulses at regular intervals during daylight hours on some stations, for example, SLMT, BGMT, are caused by the solar charging system voltage regulator. And yes, guys, that's actually possible. There is also radio noise. Since the seismic signals from the seismometers are typically transmitted to the Earthquake Studies Office using low-power FM radio news links, other radios with similar frequencies may interfere with our signal. Interference is usually very easy to distinguish from earthquakes because the interference is spiky or one-sided and begins and ends abruptly. So it actually is pretty simple to read a seismograph, guys. Now, reading waveforms and discovering their origin is a little trickier. I don't really use the online seismographs too much anymore except for quick overview to see if there's an event. I do most of my research into daily seismic events at Yellowstone using the 3 seismology tools I will talk about in part 2. Real quick, here's RER from Mount Rainier. Real quick, here is that electronic pulse that they were talking about. Now, it can look completely different than this, but as they said, it usually starts abruptly and ends abruptly, but is almost always easy to distinguish between actual vibrations, whether it be surface noise or actual seismic events underground. Yep, doesn't really look like an earthquake to me, guys. So like we saw from the article from Montana Tech, here's just a random seismograph from Yellowstone, just as an example. You read it from left to right, top to bottom, just like a book, guys, just like a book. Alright, on the left we have mountain time, on the right we have universal time, which is UTC. Now UTC is what seismologists usually use. Remember, right here is July 29th, right here. But right here it says July 29th, even though it's ahead, right? Well, UTC is a little ahead of the time zones in the United States. Right now, 0 UTC would be 5 p.m. Pacific time. Next time daylight savings time occurs, since UTC doesn't have daylight savings time, 0 UTC will be 4 p.m. Pacific time instead of 5 p.m. Pacific time like it is now. Yeah, it's a little confusing, guys. Now the time marks at the bottom. See, these are minutes. Now some seismographs have one time configuration such as RCM and Mount Rainier, which only has GMT at the bottom, which is also UTC. So they only show UTC right here on the left. There's no time period on the right either. But others have 2 time periods such as the University of Utah seismographs we are currently looking at. Now, please get used to UTC. Learn about it and get used to it because that's what seismologists use all the time. I'm completely used to it, but in the beginning, it confused me like crazy. Now, using the program Swarm, which I will show you in part 2, you can change the side and the bottom time frames. Now, why is that important? Because if we were to manipulate the bottom time frame, it would affect the length of the seismic trace, whereas manipulating the side time frame would affect the height of the seismic traces. And here, I don't know what that is. That looks like an electronic problem to me. That does not look like an earthquake. Now, if you're wondering what these letters here mean, YLT, EHG, WY, and 01, I will actually explain that right now. To start off, every seismograph in the world is connected to a network, even if only one seismograph is connected to the network in question. In order to retrieve seismic data for analysis from IRIS, which I'll show you how to do that in part 2, you must at the very least know which station from which network you want. A network code is always 1 or 2 letters, or a letter and a number, never more than 2 characters long. This here is the network. See, I have it station, channel, network, location. I have it all laid out for you. This is the network right here. Now, it is also the same network that supplies the majority of seismographs from Yellowstone. The only 2 networks I use for monitoring Yellowstone is WY and PB. PB, right here, see, PB, is the network for all UNAVCO boreholes and seismic instruments. There are also a few other stations in Yellowstone from other networks. A single network can contain either one or hundreds of stations, from either one small location to all across the globe. If you ever need help finding the correct network codes or station codes for any given location, please email me at the email address below in the description box for help. Now this here is the station code. It is usually either 3 or 4 characters long. This is the location code right here. In my experience so far, I have only ever used 3 location codes, either --00 or 01. Last is the channel code. This is the type of seismograph you will be viewing, such as short period seismographs, broadband, or long period. I will leave a link to this in the description box below. Here's a quick reference to what the first letter to a channel code means for that station. I usually use the channels starting with E or S since I am more comfortable with short period seismographs than any other type. Of course, I hope that will someday change. I do need more help with broadband and long period seismographs. Notice the short period seismographs seem to record the most detail possible. Again, here's another example of identifying a seismograph: the station, the channel, the network, and the location. Notice the location here is actually --. And here's the last example. Note how the codes on different seismographs are sometimes in different spots. However, they are usually very easy to point out. Also note the location code is missing here. You will probably have to guess, but remember the most common location codes are --00 or 01, so it shouldn't be that hard to guess. And here we are with the seismic program Jamaseis. I still don't know whether you pronounce it Jamaseis or Jamaseis. I will show you the basics of this program in part 2, the next video, which will be all about the basics of Jamaseis, swarm, and the waves seismic programs. But I want to show you the importance of knowing those 4 types of seismograph codes: network, station, location, and channel. Keep in mind, this application is very slow, so if it freezes, please don't press a million buttons or attempt to close it. Give it a few minutes and it will work, depending on your computer. Any helpful links related to part 1 or part 2 will be in the description box of both videos, along with the parts of each part. You know what I'm saying? Part 1 in the description box will have a parts section, so you can kind of mosey on through the video and see what information you want. And part 2 will have a parts section in the description box as well for part 2. Please email me if a link is missing. Now let's say an earthquake occurs at Yellowstone and you want to break down the waveforms to see if it was caused by tectonic or volcanic stress. Make sure you know the codes you need. And now you know where to find them and why. So, let's press File, Manage Sources, Add Source. Only 3 sources total are allowed at any given time. And since the more sources you have, the smaller the waveforms appear, so I usually only use about 2 at a time. I do not use remote much, which is right here, and local is if you have a personal seismometer hooked up to your computer. The bottom options I don't find very helpful, so I usually pick IRIS DMC, which is the main seismic database. Now when a source is added, you only have 3 days of data, plus any data retrieved while the source is on. I was a little mad when I found that out, but the IRIS time series program helped a lot. I will talk about that first in part 2. So click IRIS DMC. It will ask if you want to use the map view or the manual way. The map, come to find out, for me, is not really helpful. Even when you select a certain network, the detail of the globe is terrible, so it is hard to see a given location. So I usually always pick manual. If you do not perfectly know each code to enter here, make sure you at least know the network code. Then please click Full Station List. Next, it seems it will give you a list of millions of networks. In a second, I will show you the networks I use the most in my research. But for now, since the example is an event at Yellowstone, we go all the way down to the WY network. Let's say a large, shallow 5.0 earthquake just struck the location of the most recent magma intrusion at Yellowstone at Little West Thumb on the western tip of Yellowstone Lake. The best seismograph to use would be YLT. So after you select WY, then, where to go, YLT, click 01. Remember, usually the first option is what we use in regard to location codes, and click EHZ. Remember, JAMA is quite slow depending on your computer. So let's press OK. So have some patience, and then OK again. It may seem stuck at times, even when Windows says not responding, but trust me, it will eventually come around. See how no seismic traces came up? Well, you gotta give it a little bit. So now you know how to add a source to Jamaseus, which a more in-depth explanation will be given in part 2. So real quick, I will now show you most of the common networks I use in my research. And no, Yellowstone is not the only hazard area I am researching about and watching. Newberry supervolcano in Oregon is also another area I like to keep my eye on. The networks for that supervolcano are mainly the UW network and the CC network. But here is the WY network. As you can see, WY mainly covers Yellowstone and the surrounding area. The other network I find myself using a lot since I live in Washington State is the UW network, supported by Pacific Northwest Seismic Network and the University of Washington. I am actually hoping to join the University of Washington eventually as a student in volcanic or regular seismology in the next year or so, depending on what happens. As you can see, this network covers most of Oregon and Washington. Another network I use, though not as often due to the lack of short-period instruments, is CC. This network monitors some of the dangerous volcanoes in the Cascade Range, such as Mount Rainier, Mount St. Helens, Mount Hood, Newberry supervolcano. And another network I find myself using a lot is the Montana Tech Seismic Network, known as MB. Many stations are listed, such as QLMT, which I believe is this one right here. Yep, QLMT. Earthquake Lake, which resides very close to Hebgen Lake in West Yellowstone. Remember, not all stations in a single network are available for data retrieval or request. Why? I actually have no idea. Some days they are, and some days they are not. Really, I'm pretty sure the networks and the network connection to your computer on the internet is not as infallible as we'd like to think. And here is network TA that literally covers the entire United States in a sort of grid pattern, with 1,891 stations. The US network covers a large majority here as well. I believe the US network is the ANSS project. Another example is the current study of the Cascadia subduction zone off the coast of northern Washington, the NV network, and off the coast of Portland, Oregon, the OO network. So, two ends of the Cascadia subduction zone, two areas. For example, some networks have stations in many locations, such as, let me go up here, Antarctica. And look, one of the stations, I don't know if it's active or not, is literally directly at the South Pole. Pretty cool. But it also has many stations in many locations, such as Antarctica and also the PF network for eastern Madagascar, off the coast of eastern Madagascar, actually. These are just a very minute percentages of the actual network coverages of seismographs in the world in the IRIS-DMC database. Sadly, there are interesting areas of the world, such as the Mount Agung volcano in Bali, Indonesia, that does not receive IRIS-DMC coverage. However, those seismographs can possibly be retrieved by other data sources too intricate to go into right now. To be honest, I still have problems because some things about seismology and how to retrieve data sources still make my head spin. Again, patience and passion will help you through it. Well, that is it for this part, for part 1. Remember, this video started with P1, so please go to the next video that carries the same title except with P2 at the beginning to continue this if you would like. Thank you, guys.